class we will see how compensation is done and what are the different modes of compensation that we can use in fact technology. So let's start. The first one is the ideal series compensation, ideal shunt compensation. So usually, as we know that the voltage is affected more at the middle of the line, so shunt compensators can be used at the middle of the line so as to have the minimum effect on the voltage. So we can say voltage variation will be minimized. That's why I have here shown, because we know that M is the midpoint of this transmission line and we have used the compensator at this point. So let us say it is divided into two. This is x by 2, this is x by 2. The current flowing from this point to this point is denoted by IMR, and the current flowing from source to midpoint is ISM. Ideal means it is not consuming any power, it is only providing the reactive power. This reactive power can be lagging or this leading. So compensator is expected to provide a sufficient amount of reactive power so that Vs is equal to Vr is equal to Vm is equal to V. So all these voltages should be equal. So when this is the case, usually this compensator can be a synchronous condenser or any FACTS controller. So the KVL equation in this loop and in this loop are written like this: Vs is equal to Vm plus J ISM into x by 2. Similarly, Vm is equal to Vr plus J IMR plus x by 2. So this is the phasor diagram for this system, where Vm, Vs and Vr are same in magnitude. Definitely they will have a different angle. Since it is at the middle point, we know that this will be delta by 2, this will be delta by 2, and this current I is IMR, that is current flowing through this. It will be at a half angle of this, that is delta by 4. So as we have done the earlier analysis, same analysis will be applied to this case also. Only thing is that it is similar to that of the previous case. Now it looks like as we have two previous cases which are cascaded to each other. You can see from here, this one and this one same, and this is the midpoint voltage VSM, that is voltage as here, and VMR as the voltage at here. They are cascaded and placed, or we can say placed next to one each other. So from the phasor diagram, this, let us first find out this Vm sin delta by 4. That is Vm sin delta by 4 will be this much. That means half of this voltage drop. That half of this voltage drop will be equal to ISM into x by 4. ISM into x by 4. So actually, the total voltage drop is actually ISM into x by 2. The half of this will be ISM into x by 4. This voltage drop should have been IMR into x by 2. So taking ISM from here, it will be equal to 4V sin of delta by 4 divided by x. So it's very simple. It is similar to that of the earlier one. Only difference will be here. We have 4 here, we have 4 here. Other things are all the same. So one more thing that you need to be clear, that when we calculate IMR, you see that that will also be same, 4V sin of delta by 4 by x. So I can write it as IMR is equal to ISM is equal to this. Now calculate this. PR is equal to VR into IMR into cos of delta by 4. That is VI cos of theta, because now the angle between this current and this voltage is delta by 4. So that's why here it is cos delta by 4. So putting the value of IMR in place of this, we get V into 4V square by x. Sorry, 4V by x sin of delta by 4 in place of IMR and cos of delta by 4. That is the power factor. So it comes out to be twice V square by x sin of delta by 2. So PR in this case will be equal to twice V square by x sin of delta by 2. So this is how the real power transfer has changed from the earlier case. Earlier it was only V square by x sin of delta. Now the compensator reactive power, that will be equal to Vm ISM sin of delta by 4. That is voltage current sine of the angle, and this will be the same term. It will be equal to V into 4V by x sin of delta by 4 into sin of delta by 4. That will be equal to twice V square by x 1 minus cos of delta by 2. So QC will be this. We know that the reactive power supplied by the source should be equal to the compensator reactive power plus reactive power of the receiving end. So our QR will be equal to QS minus QC. But QS, as you can calculate, as we have calculated QR for this type of transmission line, when we calculate, I have not shown you how to calculate it, but as you have calculated the value of QR, so same way you can calculate the value of QS. It comes out to be, it will come definitely be, that is twice v square by x cos of delta by 2 minus 1. You can see there is only one difference, that is here is 1 minus cos delta by 2, it is cos delta by 2 minus 1. So when you calculate QR, that is QS minus QC, or we can say it will be equal to minus QC minus QS, so it comes out to be this minus 4v square by x 1 minus cos of delta by 2. I actually keep it like this in terms of this, so taken this minus outside, otherwise it would have been twice v square by x, sorry 4v square by x cos of delta by 2 minus 1. So keeping these things in mind, so when we plot this, this is the P with no compensation, its curve will be like this as we have seen earlier, and this is the P with compensation. In this case you can see its maximum value will be equal to twice P max. It has increased when delta changes from 0 to pi actual delta. You can see the power transfer delta, that is delta by 2. You can see it only changes from 0 to pi by 2, its maximum value, so it will give its maximum value. So that is the advantage of this. There will be no decreasing of the power. You'll see that this has a great advantage. I have told you in the earlier cases, perhaps in the power system second, when we discuss about the stability of the system. So here you can see twice P max, this maximum power transfer of the system has increased to twice. Now the drawback for this case is that QR has increased and its variation will be like this. You can see Q with compensation will be this much, so its maximum value will be equal to 4 P max. So what I mean to say is that in this case, even if we have increased the P max to twice P max, but simultaneously we have to increase the Q also. So that is what I am telling you time and again, that we need to have an independent control. Till now we have dependent control. When we increase the P, Q also has to be increased. From this, the maximum power becomes double, that's P max will be equal to twice V square by x, and it occurs at P is, delta is equal to pi. The reactive power supplied by the compensator will also be same as QS, and we have seen that their magnitude will be same. This QC and QS, their magnitude will be same. So that the total reactive power received by the receiving end will be twice QS. So total reactive power will be 2 times of this magnitude that we have calculated to be 2 times this. So that means we have to supply 2 times of the reactive power as at the receiving end, so that this power will increase to twice P max. So this is the variation of the voltage with respect to the distance. You can see now, since we know that receiving end voltage, sending end voltage at the middle point, they are forced to be at the same value. Other voltage will change like this. Now you can say earlier the voltage variation was like this. At every point you can see that the voltage variation was more. Now the voltage variation has decreased to a good amount. So in this case we can by using this compensation, shunt compensation at the middle of the line, voltage variation becomes this. The upper curve is for when the power is less than surge impedance loading. The middle curve is when power is equal to the surge impedance loading, and this one is the one when the power is greater than surge impedance loading. So this is very simple, you can understand this. Now if we want to increase further the power flow and make the voltage profile better, we need to use more compensators, and we have to divide this further into 4 parts, because from here you can see now the voltage variation will be at this point, maximum voltage variation, and at this point. So we can use another 2 compensation, one is at this point, one is at this point, to have a lower voltage variation like this. So here we have used the 4. The phasor diagram will look like this. This is the current I. So P, that's PR will be equal to 4V square by x sine of delta by 4. It will increase by 4 times. but simultaneously this Q, the compensate of the receiving and reactive power, will be equal to minus 8 v square 1 minus cos delta by 4. So we need to keep this in mind as well. Now with the increase in number of segments, the voltage variation along the line would decrease and approaches to an ideal constant voltage profile, and any amount of power can be transmitted from the sending end to the receiving end. So if the number of segments has increased, number of compensators has increased, we can approach to the ideal constant voltage profile and any amount of power can be transferred. But it depends upon the two very important things. That is the response of the compensator and the limited var generation. Because usually the response is not instantaneous of the generator. It takes some time to respond to the input. And var generation, that is the capacity of the compensator, is not infinite. It is capable of, it has some capacity, it has some limited capacity. So beyond which it cannot supply the or absorb the reactive power. Also, there will be a maximum limit upon which P can be increased, that is the thermal limit and stability limit. So with these constants, we need to have, we cannot go and add the different compensators at the middle of the line, at the different sections or different segments of the line. In that case, we may observe such problems, that is thermal limit, stability limit, limited power generation and response of the compensator. So this is one, we can do it up to certain level, but not up to the ideal level. So this is what I mean in the general conclusion. Now coming to the ideal series compensation. So what is series compensation? In this case, since we know that the power transfer is dependent upon the its inversely proportional reactance of the line. So when X is decreased, power transfer can be increased. So in this case, series impedance is reduced. Effectively, we can say line length is reduced. This is usually done by using a series capacitor in transmission line. When a series capacitor used in transmission line, the reactance of this and this will cancel out each other. Depending upon the value of this XC, the amount of reactance, that amount of reactance from this can be reduced. Usually we know that P is equal to V square by X sine of delta. As X is reduced, P will increase. So X effective will be definitely X minus XC. Taking X as comma, it will be equal to 1 minus XC by X. So that is equal to X into 1 minus this K, where K is equal to XC by X. This K is known as series compensation factor. Its value is usually from 0 to 1. So its value is not kept more than 1. It's never kept usually close to 1 as well. Because if you keep it equal to 1, it will result in the result. And we know that when resonance occurs between inductance and capacitance, it results in the high voltage amplification across inductance and capacitance. So to avoid that, we always keep this K less than 0.7. Now this is the phasor diagram for the ideal series compensation. This is Vs, this is Vr, and this is Gix effective, where X effective is equal to X minus Xc. So actual phasor would have been like this, J into Ix without Xc, but because of Xc and I have used half of the Xc over here, half of the Xc here. So that's why I have the voltage drop, one voltage drop over here and one voltage drop over here. That will be opposite to the inductive voltage drop. So this will look like this. This current is same as that of the earlier one. The only thing is that now it will reduce, because earlier you can know that when the delta has a lot of angle, or you can say more angle between them, it has increased. From here you will also see whether it will decrease or not. So from this will be equal to Jix effective by 2, or its magnitude will be equal to Ix effective by 2, that is equal to V sine of delta by 2. That is the sine component of this, because this will be delta by 2, will be equal to I x effective by 2. So I will be equal to twice V sine delta by 2 divided by x effective. Since x effective is equal to x into 1 minus k, so this I will be reduced. This I will actually be increased because now this will be reduced. When this is reduced, this will also increase. So this I in this case will be increased. Now I is equal to twice V sine delta by 2 x into 1 minus k. So now PR is equal to VR IR cos of theta, which is equal to V twice V sine delta by 2 cos delta by 2 x into 1 minus k. This is the value of the PR that is receiving in real power. So you can see from here, as k is equal to 0, there will be no improvement in the power transfer. When k increases, for example, k is equal to 0.5, 1 minus 1 is 1 minus 0.5 is 0.5, and 1 divided by 0.5 will be twice, it will increase by twice. So depending on the value of k, this PR, the maximum value of the PR can be increased. Now the reactive power supplied by the capacitor, that is equal to I square xc. You can see from here the total reactive power supplied by this will be I square xc by 2, I square xc by 2, total will be I square xc. This is this I. But I we have already calculated, it comes out to be twice V sine delta by 2 into x into 1 minus k. So that will be equal to 4v square sine square delta by 2. This will be x square into 1 minus k whole square. This xc is equal to k into x because k is equal to xc by x. So this x and this x will cancel out. So qc will be equal to 4v square sine square delta by 2 by x into k divided by 1 minus k square. So qc will be equal to twice v square by x because 1 2 will be consumed with this sine square delta by 2. It comes out to be 1 minus cos of delta into k divided by 1 minus k. This should be whole square. So usually what is usually done to have this series compensation, it is used to improve the or increase the power transfer capability of the system. So it has very little to do with the voltage. Of course there will be some change in the voltage, improvement in the voltage profile, but usually its more effect will be on the power transfer, real power transfer. So this curve is for P when k is equal to 0. This curve is P when P 0.2. So it will be, P max will be equal to 1.125. So this curve will be P is equal to P when k is equal to 0.4. So it will be equal to 2.5 P max. So as we increase the k, this also increase. The initial point and final point will be same because it depends upon the delta. It depends upon the delta. It will be when delta is equal to 0, this will be equal to 0. When delta is equal to pi, it will not be equal to 0. This is for QC. When k is equal to 0, QC will be equal to 0. The reactive power supplied by the capacitor will be equal to 0, and this will be the line. When k is equal to 0.2, there will be slight increase, and it will increase like this. When q is equal to 0.4, the reactive power supplied by this will be like this. So this is how the ideal series compensation can be used to increase the power transfer capability. So I think I will stop over here and will continue from the next class. Thank you.